Magnets are awesome. They're the closest things we have to magic. They've captivated people for thousands of years. Naturally occurring magnetic ores or lodestones have been sort of curiosities for much longer than anyone really had a clue what magnetism was. They revolutionized navigation, and more recently, they are really right at the heart of essentially all of modern technology. So the first thing is, what is a magnet? I mean, you guys have all, I'm sure, I hope, played with magnets at some point in your lives, whether it's a fridge magnet or a bar magnet. And to really talk about what a magnet is, it's easiest to start with a bar magnet. These are the most common kinds of magnets you find. Even a fridge magnet is a little bit like a really squashed bar magnet. Essentially what they are a bar that is a magnet. It's in the name. So they're usually rectangular prisms-ish. Some of them are like cylindrical. It doesn't really matter. The long story short is that they tend to have like a long end, a long side, and the two ends are called poles. Specifically, one is called a north pole, the other is called a south pole. By convention, if you ever see a magnet where part of it is colored in red or something about it is red, that is typically indicating that is the north pole of the magnet and the other end is the south. So far, what's the big deal, right? We've got a stick with some letters etched into it. But magnets are so fun to play with because they push and pull on each other and on other kinds of materials too, but let's just focus on magnets for now. And you might notice if you have two magnets that if you put them end to end next to each other in one way, they might attract each other, they might pull each other inwards. But if you spin one of them around, they might suddenly push each other away. And so magnets can exert repulsive and attractive forces on other magnets. Similar to how electric charges can exert electric forces that attract or repel other charges, depending on their nature. Fortunately for us, bar magnets, or magnets in general, follow a similar rule to charge in terms of what attracts and what repels. It turns out that two like poles will push each other away, they'll repel, whereas opposite poles will attract each other. So south poles repel other south poles, and north poles repel other north poles. Meanwhile, north poles and south poles attract towards each other. So if you have a configuration like the one I have set up right here, the two south poles are close to each other, the north poles are far away from each other, the south pole's repulsion will win, and the magnets will push each other apart. This is why when you flip magnets around, they can switch from pulling on each other to pushing on each other or vice versa. What makes magnets so captivating is the fact that they pull and push on each other even when they're not touching each other, even when they're separated from each other. So for example, these two magnets right here, if I put them on a really smooth table and I set them down this far apart, they would likely push each other apart. This is simply not something that is really normal in our experience. It's certainly not the only example of forces that exert or forces between objects over a distance. Gravitation does something similar, but gravitation is such a constant in our lives. It always pulls us downwards and it's always there and it never really changes. And so it's not really something that we think of as, we just don't really think about it that much. It's just part of existence. But all the other forces that we deal with, they're contact forces. They require surfaces to be in contact with each other in order for a force to be felt or transmitted. Not the only force. We've learned about another besides gravity, which is electric forces. Those can also act over distance between charged objects. The problem is that objects tend to be electrically neutral. Electric forces are very strong. And so if you do have a big imbalance of charge, it tends to sort itself out. The imbalance of charge inevitably results in, opposites attracting, and everything kind of equalizes. So electric forces tend to be very weak. For example, the largest electric force we as people ever really deal with are static forces, like the kind of force that can barely hold up a balloon. Balloons are really light. So magnets are really the only real exception, other than gravity, to this rule of contact forces that we deal with, and that's what makes them so fun. Basically, they let us pretend to be really crappy Jedi. But this gives us a big hint as to how they work. All the examples of forces that we've learned about so far that are able to act over distances without surfaces being in contact with each other are transmitted through fields. And so the same is true for magnets. These magnets are repelling each other because the magnets themselves are creating magnetic fields, and the magnetic fields exert forces on the other magnets. Magnets have some important differences from electric forces and electric charges. We'll talk about those more later, but one that we should bring up now, and we will elaborate on, is that magnets have the strange property that poles always come in pairs. A bar magnet has a north and a south pole. There is no magnet that has only a north pole or only a south pole. And in fact, we'll talk about more what would happen if you take a magnet and you break it in half. So if I want to investigate what the magnetic field created by a magnet looks like, I need to come up with some kind of test charge. If we were doing this for electric forces, I would say, let's imagine placing a positive charge here, and let's measure the force on that charge. Maybe the force points this way. In that case, the field at that point points in that direction. We can do exactly the same thing for magnets, but it's trickier. The reason why it's trickier is because there are no what we call monopoles. I cannot just take a magnet and place a north pole over here and see what direction it gets pushed or pulled. Because if I have a north pole here, I also have a south pole, and they're going to do opposite things. So this makes it a little bit more complicated. Luckily, we have a really common device that we use to measure the direction of magnetic fields. We call it a compass. And the way this works is the red needle is the direction the compass points. And so it points on Earth, right? The compass points north. And so what you would do, since this is pointing north, you would spin your compass around so that the north on your compass is over here. And that would make the east over here, and the south over here, and the west somewhere over here. And what that does is by rotating your compass so that the red needle is pointing towards the end label, it allows you to really easily just read off which direction is east, which direction is south, and so on. This works because inside the compass is usually air, or more commonly water or some other fluid, and that allows this little needle to spin really easily. And what is this needle? The needle is a magnet, right? If I'm measuring magnetic fields, I need a magnet to do that. So this this needle is a magnet. It is basically a bar magnet. It has a north pole and it has a south pole. If you've been paying attention, at this point you might be thinking to yourself, no, Mr. Ilani, you've made a mistake. Or maybe you think that you're just confused. But if you remember earlier on, I said that we usually label north poles red. That means that this side of our compass needle is a north pole. But I also said that the red labeled part of a compass is the thing that points to the north. But north poles repel from other north poles, but this north pole is being attracted to the north. So have I made a mistake? Something's not making sense here. Well, it turns out I'm not really the one who made a mistake, but you can blame it on someone, although I can't give you a name. The short story is that navigators were using compasses long before any kind of physical scientist really tried to understand what was going on with magnets. They recognized that magnetic materials had a tendency to align themselves so that one end pointed in the north direction. And that side of the compass needle, of their little magnet, they called the North Pole because it pointed north. So that makes a lot of sense, doesn't it? The problem is, later, physicists started investigating the properties of magnets, and they eventually came up with this realization that opposite poles attract and like poles repel and so on. But now they had a problem because the North Pole of the compass needle pointed north, which means the North Pole was pointing to the North Pole. Let me say that again. The North Pole of the compass needle was pointing towards the North Pole of Earth. But if they're pointing towards each other, there's kind of an attraction there, which means the North Pole of this magnet is attracted to the North Pole of the Earth. But if they're attracted to each other, that means that they are opposites, which means either the North Pole of the magnet or the North Pole of the Earth is a South Pole. And so, for better or for worse, Earth's North Pole was renamed to South Pole. Now, it is important to know that north is still north, but Earth's geographic North Pole is a magnetic South Pole, because the North Pole of a magnet points towards it, and north magnetic poles point towards south magnetic poles, and since north magnetic poles point in the direction of geographic north, that means in the direction of geographic north there must be a magnetic south. Yes, this is confusing. Yes, this is unfortunate, but it's not the end of the world. Actually, it kind of is an end of the world. Although, I mean, I guess you could always just keep going. Never mind. That was stupid. Now, the point of all this was to get to a place where we could actually use compasses to measure magnetic fields and to map them out. And the gist of all of this is that we already know that north poles point north, poles point south. But with a compass, the compass needle is aligned so that it is parallel to the field lines at that position. In other words, right here at this particular location, the magnetic field line is kind of pointing like this. In terms of directions, we say that magnetic field lines point from north poles to south poles. Oops. Which gives us something like that. In other words, it points in the direction of the North Pole on the compass, because the North Pole is pointing towards a South Pole, which would be somewhere over here. And magnetic fields, again, point from north to south, like electric fields point from positive to negative. So let's actually do that. Let's analyze the magnetic field of a bar magnet using a compass. Simulation with a little bar magnet right here and a compass over here. Again, the red side of the compass is the North Pole. It points to South Poles. So the red needle points in the direction of the magnetic field. And over here on the left, we can see that the compass is pointing straight towards the South Pole. That makes sense. This North Pole is attracted to the South Pole. And so on this left-hand side, our compass needle points to the right. So the field line is pointing to the right. On the other hand, if I move my compass, I can't move it through. If I move my compass over here, well, the field is still pointing to the right. The red arrow, the North Pole of the compass, is pointing to the right, and that's because it is being repelled by the North Pole here, and the South Pole of this compass needle is being attracted to it. So the field is pointing to the right along the horizontal. But what's happening in the middle? Well, if I move my compass up here, you see that it's basically the same. It's pointing away from the North Pole. But it doesn't necessarily always do that. For example, over here, it's not pointing away from the North Pole, right? Away from the North Pole at this point would be sort of up and to the left. But instead, it's pointing almost straight horizontally. It's neither pointing away from nor towards it, although it's mostly pointing away from it. The point is that the magnetic field lines aren't straight lines either. If I kind of have it over here, it points mostly upwards. If I move it upwards, though, it starts to point a little bit diagonal. And so as I move this in that direction, it levels out. And if I continue to move it in the direction that the needle points, it kind of wraps around. And so I think that should be a little bit evocative. We've seen fields that look like this before. And in order to actually get an idea for what this looks like, I can turn on the field, which basically, now imagine I've placed a compass all over the place. So there's a compass at each one of these little locations. And you can see that it makes a dipole field. It has this field where it points away from the North Pole, it bends towards the South Pole, and kind of has this nice, I don't know what to call it. It's a dipole field pattern. Where's the stop button on this thing? Turn on the Earth. So here I have my magnet. Here, if I turn on the Earth's magnetic field actually is basically the same as the magnetic field of a bar magnet. Just imagine that the North Pole of the Earth is the south end of a bar magnet, and the South Pole of the Earth is the north end of the bar magnet. And this is more or less what the Earth's magnetic field looked like. It wraps around in these curvy patterns, and it has more or less a dipole field. And you can see that if I'm over here, my compass points in the direction of north. If I follow this direction along the surface of the Earth, I'll end up at the North Pole, the geographic North Pole, or the magnetic South Pole. And you can see as I move along the surface, it kind of always does that. Now, as you get close to the pole, compasses get a little bit wonky. They start to kind of try to point downwards more than anything. And so navigating very near the magnetic poles with a compass really doesn't work very well. And of course, if you're at the pole, it's just going to spin around in circles because it just wants to point down. There can also be local variations. For example, if you live in a region where there's kind of like a lot of iron in the bedrock, that can affect the magnetic field. Or there can be interferences from all kinds of things. And these days, we can provide a lot of interference ourselves. So compasses are not exact, and they work best in wide open spaces. And they work especially well over the oceans where there's no nearby metal or anything to get in their way. This is another kind of magnet. It's called a horseshoe magnet, named because it kind of looks like a horseshoe. And really all it is it's a long bar magnet that's been bent. And the reason for that is if I had a really long bar magnet, this length but all straight, the North and the South Pole would be really far apart from each other, and they actually wouldn't make a very strong field overall. Very close to the poles, sure, but anywhere else it wouldn't be particularly exciting. But here, we actually get the North and South Pole of one magnet very close to each other. And so this ends up producing a pretty nice and strong magnetic field. This is the most common way strong magnets are made. These days, we can also make magnets out of more novel materials like rare earth magnets and stuff like that. But this is a really common way of doing it. Now, again, magnetic field lines point from north to south. If I were to place a compass right in the middle here, it would point directly from north to south. And so I can draw a field line that points from north to south. Now, I can also imagine if I have a compass somewhere over here. Well, it can't point away from north and towards south at the same time, right? Away from north is not the same as towards south. So it's going to be some combination, but we can think of it kind of like vector addition again, just like with electrostatics. If it's pointing away from north and towards south, horizontal bits are going to cancel out, and it's going to be pointing straight down here. But if I'm really close to north, the North Pole is going to win, and if I'm really close to south, the South Pole is going to win. And so the magnetic field will kind of bend outwards like this. And so the magnetic field of a horseshoe magnet has this kind of bendy behavior where it kind of looks like half of a dipole or something outside, but inside the horseshoe, it tends to be a pretty strong field. Now, it's worth noting that the field is often pretty weak over here, and it's very weak outside. The reason for this is basically we've concentrated the field strength in this region at the expense of everywhere else. Now, another thing that this allows us to do, and if I want to draw this to better scale, the magnetic field, just like the electric field, is usually drawn so that the closer the field lines are to each other, the stronger the field is. So in other words, we draw more field lines in regions where the field is strong than we do in more distant regions or regions where the field is weak. The same kind of analysis we can do with electric fields, we can also do with magnetic fields. Now, one important difference is if I were to place a compass, for example, over here, the needle would point that way because the needle points in the direction of the magnetic field line. If this were an electric field and I placed a charge here, the charge would experience a force. It would be pushed that way. But this magnet does not experience a force because this magnet has a north and a south pole to it. Now, because the poles of a compass needle are really, really small, they're more or less equally affected by the magnetic field around them as each other. They're basically in the same place as each other, as distinguished from, for example, a horseshoe magnet where they're in very different places. In other words, the net force on a compass needle will be essentially zero because each pole will experience a more or less equal and opposite force. So compasses don't get pushed around by magnetic fields. They do get twisted by magnetic fields, though. Because, for example, if my north end is being pulled this way, and my south end is being pulled this way, if I were to take this compass needle and try to twist it, so if I were to physically push on the needle so it were like this, the south end would still be pushed this way, and the north end would still be pushed this way. That won't create a net force, but it will create a net torque. And that's why compass needles spin rather than swerve, actually slide around. To finish this video up, I want to talk about what happens if you take a bar magnet and you split it into two. And what's interesting is that if you do that, you find that instead of having an isolated south pole and an isolated north pole, you simply create a new pair of poles so that you have two smaller bar magnets. And if I were to take one of those bar magnets and split it into two again, I would once again end up with two even smaller bar magnets. And I can continue to do this process as my bar magnets are getting smaller and smaller and smaller. And eventually, I end up with simply two layers of atoms left. And if I split that again, I still have to end up with a north and a south pole. The atoms in one layer are not different from the atoms in another layer. And so when I split up those two layers, I'm left with two layers of single atoms. Each one has a north and a south pole. And so the conclusion that we can draw from this is that the atoms making up a magnet are themselves little magnets. This inherent magnetism of the individual atoms, in other words, it helps explain where magnetism is coming from, at least to an extent. We can still ask where is that coming from. We will get to that another time. But it's not enough because the most common magnetic material is iron, and most iron is not magnetic at all. So what's the difference between magnetic iron and non-magnetic iron? It's made out of all the same kinds of atoms. Iron atoms are indistinguishable from each other. So what makes one piece of iron magnetic and another not magnetic? Well, the key is what we call magnetic domains. Essentially, in some pieces of iron, the atoms, each of which is a little bar magnet, are all mixed up. They're all pointing different directions. And so their magnetic fields end up canceling each other out. For every magnet pointing one way, there's another magnet. For another atom pointing one way, there's another atom pointing the other. But in magnets or magnetized iron, all of the little atoms are pointing in the same directions as each other, or at least most of the atoms are pointing more or less in the same direction as each other. The way to make a non-magnetic piece of iron into a magnet is to apply a magnetic field to the non-magnetic piece of iron, because all of these little atoms are themselves little magnets, and so if we were to place a strong magnetic field in the presence of this particular piece of iron, all the little atoms inside here will have a tendency to start to be turned by a net torque until they're lined up with that external field. And so if you apply a strong magnetic field to a piece of iron for long enough, all the little atoms will eventually kind of turn until they're all lined up, and now you have a magnet. And it will stay a magnet. Once the atoms are all lined up with each other, they will actually remain lined up with each other. If you leave the magnetic field there long enough, if you apply a weak field for a small period of time, it will cause the piece of iron to be like temporarily magnetized, kind of like polarization, but it won't last because they don't line up enough. And if they don't line up enough, it's not hard for them to kind of go back to doing their own thing. But once you get them to be mostly pointing the same direction, it actually takes energy to sort of break them up again. So this actually leads to another question. How do you take a magnetic piece of iron and demagnetize it? There are two ways of doing this. One is if you have like good instrumentation and you can measure things carefully, you can always apply a magnetic field going the opposite direction of the magnetization of your magnet, and that'll slowly push them the other way. But if you do it this way, you have to be careful to remove the external magnetic field before you just remagnetize the magnet going the other direction instead. The most common method of demagnetizing a piece of metal is to heat it up. If you heat it up, you supply more energy to the atoms inside the material, and that energy causes the atoms, or enables the atom to jiggle and wobble about more and more. And eventually, if you give them enough thermal energy, they have enough energy that they can easily break these magnetic sort of bonds holding them in place, and they can revert to something more like this. So if you heat up a magnet, if you actually have a magnet and your parents are amenable, you can always take a magnet, place it in a stove, or in an oven, I should say, and heat it up to a few hundred degrees, and you'll notice that your magnet's not much of a magnet anymore when it comes out. Do not put a magnet in a microwave. Microwaves operate with strong magnets. Do not, under any circumstances, put a magnet in a microwave. Also, putting metal in them, just don't do that. If you want to actually do this little experiment, consult your parents about putting one in an oven, and only in an oven. Actually, another way that you can demagnetize a magnet is by hitting it really, really hard. If you like bang on a magnet once, not much is going to happen. But every time you hit a magnet, you're actually giving a little bit of energy to it. You're jolting it. And every time you jolt it, you can actually dislodge some of these atoms and they can maybe wiggle the other way. And so if you actually take a hammer and you bang on a piece of magnetic material, you'll actually end up removing the magnetism. It is technically a little bit more complex than this. The atoms don't kind of all do their own thing, but instead the atoms kind of clump together, and that's what we call these domains. A domain is a clump of atoms within a material that kind of act as a unit. And it's really these units of atoms, composed usually of like many billions of atoms at a time, although it can be less too. It's these units that align and disalign. But within a particular unit, pretty much all the atoms remain aligned, even in not a magnet. And that's it for this. This is a basic introduction of kind of how magnets work, how permanent magnets work, I should say. Next time, we will actually delve a little bit deeper into what actually causes magnetism in the first place. Because unlike electric charge, which is simply a fundamental property that things have or don't have, magnetism is a little bit more complicated in where it comes from, and we can actually probe a little bit deeper. All right, I'll see you all next time.